Good afternoon. We're picking up the second half of Chapter 2 today. Chapter 2 deals with chemical bonding, and this afternoon we want to talk about molecular bonding. We talked about atoms last week. We're going to put atoms together to form molecules. Two types of chemical bonds, the ionic and the covalent bonds. Ionic bonding involves a loss of electrons or a gain of electrons. The atoms that swap electrons are then charged. One is positive, the other is negative, so these opposite charges are attracted to one another. Covalent bonding, on the other hand, involves sharing of electrons between two atoms. And in order to understand bonding, we need to have a pretty good idea of where electrons are located in atoms so we can understand better how these atoms fit together. We talked last week about orbitals, the S and P and D and F, which I didn't put up. Gives the probability that an electron is in that area of space. And we're going to focus on S and P orbitals. We're not going to get involved with bonding involving D or F orbital. Reminder that the p orbitals, there are 3 p orbitals, each of which can hold a maximum of 2 electrons, and they're geometrically distinct from one another. They're oriented differently in three-dimensional space. Types of bonding. Ionic bonding, one or more electrons are given up by an atom and they go to another atom. They form an ion, a charged particle. And covalent bonding, on the other hand, involves electrons shared between two atoms. So ionic bonding, there's a movement of electrons, and the bonding is based upon opposite charges attracting one another. Covalent bonding, there's a sharing of electrons between the atoms. Now we talk about core and valence electrons. Core electrons are those that occupy the same orbitals as the nearest smaller noble gas atom. The core electrons are not involved in either ionic bonding or covalent bonding. So they're needed to balance the number of protons, but they do not get involved in either types of bonding. The valence electrons are those outer shell electrons, and these electrons are involved in forming bonds. They will either shift to give up or take on electrons in ionic bonding, or they'll be shared electrons in covalent bonding. Now, a lot of the elements will form ionic bonding. This particular group of elements is quite often involved in covalent bonding: hydrogen, carbon, nitrogen, oxygen, phosphorus, and sulfur. We'll see that these compounds are involved in covalent bonding. In fact, there's an entire class of chemistry involving chemistry of carbon, which is called organic chemistry, where the carbon is covalently bonded to hydrogen, nitrogen, oxygen, and to a lesser extent phosphorus and sulfur. Okay, if we look at the carbon atom, we see the core electrons. There are 6 electrons in carbon. The inner shell, the 2 in the 1s orbitals, are same as the helium atom. So we simply indicate that as having the same configuration as a helium atom, and we focus on the valence electrons, 2s electrons and 2p electrons. These 4 electrons are going to be involved in covalent bond. Chlorine atom has the electronic configuration of neon, which is the next smaller noble gas, and it has 7 electrons in its outer shell. So there are 7 valence electrons for chlorine that get involved in bonding. Now, ions can be formed when an atom gives up an electron. These examples, all of these 3 atoms have S1 electron. Lithium has a 2s1, sodium a 3s1, potassium a 4s1. They have 1 electron in that valence shell, and they can give that up to form a 1+ charge, a positive charge, form a cation. Chlorine, chlorine, and bromine have 7 valence electrons in their outer shell. And bromine, of course, is a little weird. It's got those d electrons that we don't like to talk about. But in each case, they take on an electron to form a complete octet, a complete outer shell of 8, and they have a negative charge. And this indicates an ionic compound. Lithium forms a positive ion, fluorine forms an anion, the fluoride anion. The positive and the negative charges attract one another, so we have an ionic bond. The alkali earth metals, that column 2, have 2 electrons in the outer shell, and they give those up to form a +2 positive charge cation. And here we have magnesium giving up 2 electrons to 2 chlorine atoms, forming a magnesium 2+ and 2 chlorine minuses, so we have MgCl2. The 2+ matches with 2 of the 1- chlorine. Hydrogen ions are kind of a unique thing, and we'll be talking about them later when we get to acids and bases. The hydrogen atom has 1 electron and 1 proton, so it has a half-filled s orbital. When it gives up that electron, it has an empty s orbital, and that has some interesting implications in terms of how hydrogen behaves. When hydrogen forms covalent bonds, that 1 electron is shared with other atoms. Now, ionic compounds often dissolve in water. If we look at the structure of sodium chloride, we see that the sodium ions and the chloride ions are interspersed among one another. A sodium ion is surrounded by several chloride ions. Picture more chloride ions in front of the sodium and behind it. And the chloride ions are, of course, surrounded by the sodium ions. When water is added, the water surrounds both kinds of ions. We talked about that last week. So that these things will dissolve in water very easily, and will no longer be sodium chloride, but sodium ions and chloride ions separately. Okay, covalent bondings, as I said, involve a sharing of electrons between 2 atoms. When compounds that are covalently bonded are dissolved in water, they don't separate like ionic compounds do. They don't come apart because the electrons are shared between the 2 atoms. A covalent bond is much stronger than an ionic bond. Now, we'll start talking about how these covalent bonds can be formed. The simplest molecule, H2, hydrogen gas, is formed by the combination of 2 hydrogen atoms. Each one of these has a 1s electron, a 1s1 orbital, and they overlap. The electrons are shared, so the result is a larger electron cloud around the 2 nuclei, and this is a sigma bonding orbital forming H2. So the 2 electrons are somewhere in that green cloud, sharing between the 2 electrons. Pi bonding, we have p orbitals. This is 2 p orbitals side by side. You recall that p orbitals have this dumbbell-shaped lobe, and when they overlap, they form a pi bonding orbital. So we have electrons above and below the plane of the atoms, and this bond turns out to be a very reactive bond. Now we have a situation called hybridization that quite often takes place that explains why certain compounds look the way they do. In this case, in beryllium hydride, we have BeH2. And what we have for beryllium in the ground state has 2 1s electrons and 2 2s electrons. Okay, the 2s electrons are the valence electrons, the 1s electrons are the core electrons, and are not going to be involved. We can consider that In the excited state, when compounds react, you have to get them excited. You put in energy into the system. And we assume that one of those 2s electrons is elevated to a 2p configuration. So you get a 2s orbital and a 2p orbital, and those merge together to form what we call 2sp hybrid orbitals. And it looks like the dumbbell shaped sort of a thing on the top of the page. So by doing this, beryllium can react with two hydrogen atoms, one on the kind of reddish orange lobe and the other on the sort of yellow green lobe, to form beryllium hydride. Now note that beryllium hydride is a linear compound, and we'll talk about that in a minute. Another situation can come when you react boron. Boron has, in the 2s, it has two 2s electrons and one 2p electron. Okay, these are all valence electrons. These are the outer shell. And in the excited state, one of those 2s electrons can be elevated to a 2p situation. And so we have the situation that you can see on the top of the page, where these hybridize to form three orbitals, and they can overlap. And borane, BH3, has the three-sided shaped configuration. Carbon, as I mentioned, is very reactive. Carbon has two 2s and two 2p. The 2s electrons both can be hybridized into the p levels, and you can form what's called sp3 hybrid orbitals, and we have a tetrahedral configuration, as you can see, for methane. Now, keep in mind that covalent compounds have a three-dimensional shape, and this shape, as you, I hope, have been able to pick up, is influenced by hybrid orbitals. And I've shown you the shape of the glucose molecule in the picture down on the left-hand side. Tried to represent it, but that's due to the bonding between the carbons and the hydrogens and the oxygens. Now, there are more examples. Read Appendix B at the end of the textbook, and you can get more details and get examples. So, we've talked about ions form when atoms gain or lose electrons. Ionic compounds are made up of oppositely charged ions that attract one another. Covalent bonds involve a sharing of electrons, and atomic orbitals hybridize to form molecular orbitals. That's a quick summary of a lot of details. The molecular shape is influenced by the orbitals. And that's it. If you have any questions, please email me, and I'll see you later.